Hello, this video is about how to add vectors using a table method where you break things into components and then you put all the x's together, you put all the y's together, and then at the end you slap all of them back together into one triangle. So let's see how this is going to work. Suppose I have vector A and that is, I don't know, let's go B down this way. C is up and to the left. Okay, so we've got three vectors. And suppose we want to add them as vectors. Vector A plus vector B plus vector C. You can add them graphically, where you use the tip to tail method. So you do A, but you do it much more precisely than this. And then B, and then C, and then the final vector would be something like this. Oh gosh. So the vector A plus B plus C would be like that. So that is one way to do it, but that requires ruler, protractor, that kind of thing. So I want to talk to you and show you a way to do it that is mathematical and will give you exact answers. Okay, so we have three vectors, and let's just say this is 35 degrees, and the magnitude is 2.1, we'll call it meters. Here, vector B, that's a pretty big angle. Let's say it's 78 degrees, and it's a little bit smaller. Let's call it 1.8 meters. Oh, let's go 42 degrees, and let's make it real short. You know what? Let's make this one real small. So we'll make this 0.9 meters. All right, what we want to do, we want to do A plus B plus C, but we're going to do it in a way that is numerical. And the way to do that, what we do is we're going to make a chart, and we're going to have our vectors A and B and C, and we're going to break up these vectors into the x component and the y component of each of them. Now I'm going to need more space. So for each of these three vectors, we want to figure out the horizontal piece of it, the vertical piece of it, and then same thing, horizontal, vertical, horizontal, vertical. So B and then C. So I've got my three vectors, and my first step is to figure out what's the left-right part, what's the up-down part. So if we start with A, all right, so this is the x component, this is the y component, and if we look at the angle, this is my angle here, this side right here, that is the side adjacent to the angle. If I look at SOHCAHTOA, which one involves the adjacent and the hypotenuse? Adjacent and hypotenuse? Cosine. All right, so the cosine of 35 would equal my x component, the adjacent side, over my hypotenuse, 2.1, which means my x component is 2.1 times the cosine of 35. So in this case, I can put here the x component is 2.1 times the cosine of 35. All right, y component. Y is opposite, so I know I'm looking for the opposite side, and I know the hypotenuse. There is my sine. The sine of 35 would equal y over 2.1. My y component is equal to 2.1 times the sine of 35. There's my y component, 2.1 times the sine of 35. Okay, now I'm going to use this shortcut. I'm going to just say, okay, this is the adjacent, that must be the cosine component, and then I can write it like this. This is the opposite side, it's the sine component, I can write it like this. I'm going to skip doing this step every time because that's just the same every single time. So I'm going to jump to this format. Hypotenuse times sine, or hypotenuse times cosine. Okay, so then let's look at B. Here is my x component, here is my y component. My x component, careful here, my x component is opposite the angle. So for B, it's going to be 1.8 sine of 78. And the y component is adjacent. That's my cosine component, 1.8 cosine 78. All right. How about for C? There's my x and there's my y. X is adjacent to the angle, so 0.9. Adjacent is the cosine component, 42. And y is opposite the angle, 0.9 sine of 42. All right, so there we go. Now we can just grab a calculator and do the calculations. All right, so I did the calculations, and here are my components. So for B, the left-right component is 1.76 meters. That's 1.76 meters here. Does that seem reasonable? Yeah, because it's a very flat angle, so most of it's going to be on this side. And the other component is 0.37. Yeah, not much going up down there. But we've got a problem here. That's going to the left and down. When we do it this way, if you only draw your triangle like this and only take into account that little inner angle, you have to manually put into the chart your x's and your y's, your sines. So then you go back and you look at your original triangle and say, okay, this is going up and to the right. So I have to the right, which is a positive x. I have up, which is a positive y. For B, I'm going down, which is negative y, and then I'm going over to the left, negative x. C is left, which is a negative x, and up, which is a positive y. So you have to be careful if you just do these little tiny triangles to stop and say, oh, wait, I have to add the pluses and minuses. If you don't want to have to do that, then for every single triangle, what you'll want to do is use the angle from 0. So 0, 90, 180, 270. So for this one, it would still be 35 degrees. But for B, so we'd go all the way over to 180 and then add 78 to that. So we'd be just short of 270. We'd be at 258 if I'm doing this right. I think it's 258. So we'd use 258 in here and here, and that would pop out these negative signs for you. For C, okay, we'd go 0, 90, 180, and then subtract 42. So 180 minus 42. So for this one, we would use 138. And so again, if you do 138 here, you would get out this negative and this positive. If you just do the little triangles like I tend to do, then you have to remember to put them in yourself. So keep track of it. All right, now that we have all of our components, what we do is we do the sum. Okay, and to do the sum, we're just literally adding up these pieces. I'm going to add the, let me just put them on here, 1.72 and 1.20. I did those two, and here I've got 0.67 and 0.60. So I'm going to take the 1.72 to the right, add a 1.76 to the left, and then a 0.67 to the left. And so I'm just adding these three up, and let's see what I get if I add those up. I get a 1.72 plus, oh, that's not right. 1.72 plus a negative, so I'm going to subtract 1.76 plus a negative, I'm going to subtract 0.67. Oh my gosh, that didn't work. 1.76 minus 0.67. Okay, negative 0.71, does that make sense? Well, yeah. I mean, this one alone balances out the rightward part of that, and then I'm adding more to the left, so that makes sense. And then in the y direction, I've got 1.20 up, 0.37 down, 0.60 up. So I'm going to add 1.2 minus 0.374 plus 0.68. And here I get a positive 1.43. So that's 1.8 minus 12.4. That seems reasonable. Okay, so that is the next step to figure out the sum of the x's, the sum of the y's. What you just figured out is the combination of all three of these vectors, the total left-right part of the combination, and the total up-down part of the combination. So now what we can do is put these two together into the final triangle to figure out what the final vector looks like. Let's see if I can fit it in right here. So here again, we have to be very cautious about our signs. So I have a negative x and a positive y. I should be going to the left and up. And if you rewind to the graphical method, that was left and up for the final vector. So good, makes sense. Okay, so I'm going to walk 0.71 to the left. And then I'm going to walk 1.43 up. My final vector is going to be this. So A plus B plus C is going to be up and to the left. Now, that's the vector. We want that vector. We don't want it in component form. We want it in vector form, which means we need to know the magnitude, the size, which is the hypotenuse, and we need to know the angle that it's at. So I need to know the angle and I need to know the hypotenuse. Now, why didn't I do the negative here? Well, that negative here just tells me left. For the math in this triangle, I'm going to do the squares. The negative is going to just, you square negative, it comes out positive. So I like to just ignore the negatives because if I did a negative 71 here, I wouldn't know what I was talking about. This left tells me it's negative, but then if it's a negative left, would that be a positive? Would that be a right? So I don't include the negative signs in my final triangle because what I want is just left and up. One common mistake that people make in doing this step, so I almost hate to draw it because I don't want you to think about this, but it's to draw left and up and then do this. But stop and look at your components. The vector must be left and up. This, neither one of this, it could go up and to the right or down and to the left. That is not correct. So always think about it like you're walking. I am walking to the left and then I am walking straight up. I don't go back to the beginning. No, I walk this way, then I walk that way. So keep that in mind. So to figure out this vector, we're going to use Pythagorean theorem. So 1.43 squared plus 0.71 squared and square root that to get the magnitude. All right, what do we get with that? All right, so that tells me this side, the hypotenuse, is 1.6 meters. That's my magnitude. How can I get the angle? Well, I know all three sides of the triangle now. So if I know all three sides of the triangle, I could use the sine, the cosine, the tangent. Personally, I like the tangent because these are the two sides that I know this was calculated off of these two. So I like to use these two sides. I'm using the opposite and the adjacent. So I'm going to think about using the tangent. And how do I do that? Well, okay, so we know our hypotenuse. Now I am going to do the tangent of the angle is opposite over adjacent, 1.43 over 0.71. How can I get rid of the tangent? Well, this is one chunk. You can't divide by a tangent because what would that even mean? You divide by the tangent of nothing. No, tangent always has to be of something. So to get rid of the tangent, what we do? Inverse tangent of both sides. All right, so inverse tangent of both sides, 1.43 over 0.71. This is getting messy. Inverse tangent and tangent cancel each other out, leaving me with my angle will be the inverse tangent of 1.43 over 0.71. Okay, so if I did this to scale, this is like a 1 to 2, 1 to 2. So this angle should be more than 45. More than 45. So I get 64 degrees. So 64 degrees. The final answer that I would be looking for what the vector a plus b plus c is, I've got to do it in vector form. So the final answer is 1.6 meters at 64 degrees. I can't just say 64. What 64? It could be this 64, it could be that 64, that 64, that 64, you know, you get the point. So how can I describe what this is? Well, there's a couple of different ways to do it. The easiest is probably just to think about it in that coordinate system that I just happened to erase, 0, 90, 180. We're going up here at 64 degrees there. So it's going to be 180 minus 64. So you could say at 180 minus 64, 116. Or you could say at 64 degrees above the negative x-axis. You could say 64 degrees north of west, because that would mean we're looking west and then we go up 64 degrees. Those would all be answers that I personally would accept. This is probably going to be the most common way people will want it, is that 116 degrees. So that is the way to do vector addition using this table method, and it works for any vectors. So you could use this for position vectors, you could use this for velocity vectors, for force vectors, for momentum vectors, for anything that is a vector where you want to add multiple vectors together. This will work. And it's easier. Personally, I think it's easier than the graphical method because I don't keep a protractor and ruler handy, where I always have a calculator. So there you go. Thanks for watching.